So, first of all we will discuss about if a structure is subjected to torsional types of moment and combination of torsional types of moment and bending moment, then how to design that component. So, first of all I will discuss about once a welded joint is subjected to a torsional moment, then what is the criteria to find out the dimension of a weld, or what is the criteria generally we use to what is called follow for designing those welded structure. Okay. First of all that I will discuss, then I will discuss once a structure subjected to bending separately. After that, once it combinedly subjected both torsional moment as well as bending moment, then how to design those structure in details I will discuss. So, let us consider a shaft of circular cross section you see, which is subjected to a torsional moment MT I have shown here. This shaft is, you see, this shaft is welded to its platform by using a fillet weld. This is a fillet weld. Now, I have already told you a fillet weld how it's look like, little bit here I am showing, then it will be very clear to you. So, a fillet weld looks like this, it has a triangular types of shape you can see. So, you see this is generally called as face, this is called as toe, from here to here this is called as leg I am representing in terms of ace, and this is another leg. Generally here we will consider the leg length, both the leg length is same ace, and the distance from perpendicular distance to face to this corner point is called throat thickness T. So, T is called throat thickness. So, generally this is the weakest zone, you can say this throat thickness surface is the weakest zone of this fillet weld. So, most of the failure mainly occurs in this what is called weakest zone, this you should keep it in mind. Generally there is a relationship between what is called throat thickness versus leg length. Generally dimension of a fillet weld is considered as its leg length, this you should keep it in mind. Now, the relationship between this throat thickness and leg length, ace is both ace is same. So, this angle will be 45 degree. So, if you take sin 45 degree, then this sin 45 degree you can write as what is called T, which is perpendicular divided by its hypotenuse will be ace. Okay. So, you can write ace is equal to T by sin 45 degree. So, what are the things we are getting? T divided by sin 45 means 1 by root 2. So, you can write as T divided by 0.707, T divided 0.7, this you should keep it in mind. Okay. So, generally most of the failure due to what is called in fillet types of joint is occur in this throat section, throat cross section area. That is why generally here we will consider this, whatever the weld section we are showing, let us consider this is the weld. Here let us consider the throat cross section I am showing, which is around the shaft, this is the shaft, around the shaft generally we weld it with this base, this is your base plate, with this base plate by fillet welding. That means there is a triangular types of weld we use. Now, once this shaft is subjected to torsional types of moment, then what happens, this throat cross sectional area, of that fillet weld will be subjected to a shearing effect. Okay. That is generally called torsional types of shearing stress. What it is called? here there is a torsional types of shear stress tau t I am considering. There is coming a torsional types of shear stress, because this is the throat cross section flat area I have generally drawn here, which is generally done around the shaft. You see, around the shaft, that is why you can say this is a annular weld section. What it is called? This is also you can call as annular weld throat section. This you should keep it in mind. So, here I am not going to discuss in details about what is called torsional theory, because based on theory of torsion we know this is the concept of solid mechanics. You know these things very well, theory of torsion. So, according to theory of torsion we know what is called maximum shear stress tau t equal to, you can say tau t divided by r equal to T by J. J is the polar moment of inertia, or mt you can say here, you can say T torque, or you can write as, this is also write as or T, or you can say mt. Here we consider moment due to torsion is equal to your g theta by L. These are all very well known concept to you. So, I am not going in details about these things, where r is the radius of the shaft, tau is the, you can say maximum shear stress, that you can say, then J is the polar moment of inertia, POI I am writing polar moment of inertia, G is called what is called modulus of rigidity or shear modulus of elasticity. Here I am writing modulus of rigidity. You know these things very well. L is the length of the shaft, length of shaft. Then theta is twist angle, twist angle. You know this thing very well. I am not going in details about this thing. So, to find out this what is called shear stress due to torsion, what are the things required? We need to know applied moment due to torsion, or you can say it is also called torque divided by J equal to your tau t divided by r. So, to get this thing shear stress due to torsion, what are the thing required? mt r divided by J. These are the things required. That means, this polar moment of inertia we need, then shaft radius we need, and another things we need, that is generally what is called mt, which is the torque for this annular fillet weld throat section. This you should keep it in mind, which I have shown in figure number 2. So, for finding out these things, polar moment of inertia in case of circular annular section, here I have already shown this section. What here again I am drawing this section, then it will be very clear to you. So, let us consider this is the annular throat section, this is the annular throat section. Let us consider here the axis system is, this is our z axis, that means along the axis of the shaft is z axis, and the cross section have horizontal axis is x and vertical axis is, let us consider, is y axis. Now we know that polar moment of inertia J is equal to your I x x plus I y y. So, this also you know very well. So, I am not going in detail to discuss polar moment of inertia J, which I need to first calculate for this annular section. For that actually I am taking a small element, on this what is called on this plate throat area. This, let us consider this a small element have a area dA which makes an angle with x axis is let us consider is theta. Now, this a small element, let us consider this a small element. This small element, let us consider it makes an angle theta with x axis and let this small elements makes an angle d theta here. Okay. So, this is our delta A. So, delta A, so what is moment of inertia, that means Ixx is called generally second moment of inertia about x axis, Iyy is generally called as second moment of inertia about y axis. That means, you can say moment of inertia about x axis, this is moment of inertia about y axis. Okay. So, delta A we can write as let us from here to here about y axis, the distance is let us consider y. Y we can write as what? R, you see, let us consider this r is the radius, that means r is the radius of this shaft. So, you can say r sin theta, we can write y equal to r sin theta. Delta A you can write as r d theta into what? This is the throat thickness, let us consider this is the throat thickness, that this is our T is equal to throat thickness of the fillet, because at throat thickness only our sharing will be occur. That is why this throat thickness cross section we need to consider, that second moment of area we need to find out. So, r d theta into T is the delta A. So, what is Ixx? So, Ixx we can find out what? First we find out what is delta Ixx, a small for this a small element, what is delta Ixx. So, delta Ixx you can write as delta A into distance square from this x axis, that means distance square means here y square. Okay. So, this I am writing here delta A I am writing as r d theta into T, and y square means you can write as r sin theta square. So, what will be the Ixx, total Ixx? So, Ixx will be you can write as integration of, you can say minus pi to plus pi, or you can say 0 minus pi to plus pi, this you can write as 2 to 0 to pi, okay, 2 into 0 to pi this delta Ixx, okay. This you can write as 2 into integration of 0 to pi this r q t sin square theta d theta, sin square theta d theta, correct. This we can write. So, if we just do the integration part, let us see this Ixx here I am writing, that will be better. So, Ixx what we are getting 2 into integration of 0 to pi T r q, okay, T r q sin square theta d theta, this we can write, correct. Now, these things generally what we can do, this thing we can write just if we do little bit calculation. So, 2 t is constant, r is also constant, okay, integration of 0 to pi. So, sin square theta I am writing as 1 minus cos 2 theta by 2, 1 minus cos 2 theta divided by 2. This is very well known to you. How it is coming, that also I am, because I am not skipping a single steps, because then you will face problem. So, these things you know, cos square theta minus sin square theta is equal to cos 2 theta. So, based on these things and sin square theta and sin square theta plus cos square theta equal to 1, based on these two formula generally you can find sin square theta equal to 1 minus cos 2 theta by 2. So, this if you just do the integration, what are the things you will get? You will get 2 t r cube, you can write theta by 2 minus sin 2 theta by you can say 4 whole to the power 0 to pi. Okay. So, this will give you a value, that is 2 t r cube into pi by 2, because this sin 2 theta 0 to pi it will be 0. So, that is why only pi by 2 will be there. So, this is actually you can say pi t r cube, its unit is millimeter to the power 4 or millimeter to the power 4, millimeter to the power 4, this you should keep it in mind. Now, what is j? So, we know j is equal to, as it is a symmetric types of section, you can see this annular fillet section, it is symmetric about x axis and y axis. So, here I y y also due to symmetricity you can say I y y is equal to also I x x, that is also equal to you can write as, that is also you can write as pi t r to the power cube. So, what is j? So, according to the formula of j, we know j is equal to, we know as what? J is equal to your I x x plus I y y, 2 I x x you can say due to symmetricity. So, 2 into I x x is equal to you got as pi t r cube, this you should keep it in mind. So, j you got, this is the main things you need to calculate for this weld joint subjected to torsional moment. Then you can easily find out according to the formula, according to the formula you can say of equation number, let us, this is equation number 1, this you can easily find out what is tau t equal to, once j is known, tau t you can easily find out as mtr by j. Okay. Now, one problem on this I will just solve first, then it will be very clear to you. So, whatever the problem related to weld joint subjected to torsional moment, for this actually how to design a structure, that I am going to show. Okay. So, here generally a circular shaft which is earlier shown in previous slide. Let us consider a circular shaft. Okay. Let this is a circular shaft which is subjected to, this has a diameter is given as 50 millimeter. Okay. Now, is welded, here it is welded, here generally it is welded, this circular shaft here it is welded, fillet welding is done here, generally is welded to a support by means of circumferential fillet weld. This circumferential fillet means around the shaft this welding is done. Okay. It is subjected to a torsional moment. So, it is, let us consider it is subjected to a torsional moment mt, which is equal to your 2500 Newton meter. Now, what are the things we need to find out? We need to determine the size of the weld. So, size of the weld means, size of the weld we need to find out, size of the weld. So, what is size of the weld? I have already told you is, that is your leg length, this leg length generally we have to find out what is this leg length. Considering the permissible shear stress of the weld is 140 MPa, that permissible stress is given it, that means here tau max or you can say tau permissible or tau allowable is generally is given as what 140 MPa. This you should keep it in mind. So, these are the things given. So, you need to find out size of the weld ace. So, now I am going to solve this problem. So, in previous slide itself I have shown you generally the shear stress developed due to torsional moment MT is equal to we know MT R divided by J. These are the things already I have shown you. So, here MT is given as 2500 Newton meter. So, this I am converted into Newton millimeter. So, 10 to the power 3 I am doing. Here radius of the shaft, diameter of the shaft is given as 50 millimeter. So, radius of the shaft will be diameter by 2, that means 25 millimeter. So, this 25 millimeter I have written here. And what is the J here we got? J already I have shown you, that is generally 2 into throat thickness into pi r to the power cube, correct. These things already I have shown. So, this just I am putting this value. So, 2500 into 10 to the power 3 I am converting into what it is called millimeter, Newton millimeter, because it is given as Newton meter, that is why I have multiplied 10 to the power 3. Radius is 50 millimeter by 2, that is 25 millimeter, divided by 2 t pi r q is given as 25 to the power q. This is the torsional shear stress. Now, this torsional shear stress we need to find out first T, throat thickness. What is the throat thickness? Based on what? Our permissible shear stress value. So, here the permissible shear stress value is given as tau p is given as. So, this shear stress will be equated with permissible shear stress, that is your 140 Newton per, this unit is Newton per millimeter square. This you should keep it in mind. So, from here if we calculate based on this equation, what we will get? We will get T is equal to 4.55 millimeter. Now, we need to find out size of the weld. So, size of the weld, just in previous slide I have shown you, in case of fillet weld, size of the weld is generally, you know, formula already I have already, H is equal to T by 0.707, correct. These things already I have told you. So, this you can write as 4.55 divided by 0.707, which will be equal to what? 6.43 millimeter. So, you can consider this thing, but what happens? It is better to consider a little bit higher value of this size of the leg length. You can consider instead 7 millimeter. This instead of considering 6.43, if you consider little bit higher value, then you will be further more reserve side, you can say you will be in more safe side. That is why what happens, you can consider 6.43 millimeter itself, but what happens if you consider little bit higher value of next digit, then what happens, that is also applicable. Okay. So, this here size of the weld you can consider at 7 millimeter. So, this is once a welded joint subjected to torsional moment. Now, I will discuss about welded joint subjected to bending moment. So, bending moment, in the bending moment case generally there is a let us weld let this is a shaft or a beam, you can say, which is subjected to this circumferential types of, you see this shaft, if it is 3 dimensional case, if you take the cross section, you will get, this is the shaft diameter, outside this shaft diameter you see there is a, you see, let this is the weld cross section, let this is our weld cross section at throat area, Okay. This I am just showing. A welded structure here I am showing, which is subjected to a, let us cantilever types of beam subjected to a load P here. So, this P here is given as let us 10 kilonewton, P equal to 10 kilonewton is given, okay. And it is subjected to a fillet weld. I have already told you this is generally a throat cross sectional area. Now, here the length of this cantilever beam, you can say cantilever beam, because it is subjected to bending, correct. That is why cantilever it is called as beam, 200 millimeter. Now, we need to find out what? We need to find out the size of the weld if the permissible shear stress is limited to 100 MPa. Okay. This you should keep it in mind. So, due to this bending load, point load you can say P, we need to find out what is the size of the weld, because here this you can say beam is subjected to bending. This you should keep it in mind. Now, I will solve this problem now. So, here what are the things given? Force P is given as 10 kilonewton, length of the beam is given as 200 millimeter, tau permissible is given as 100 MPa, okay. MPa, we need to find out what H is equal to leg length, H is equal to what, okay. So, for finding out these things, what are the things required to do? We know, actually I am not going in details from the theory of bending. According to, you can say pure bending theory, what we know? We know bending moment divided by I is equal to your sigma B bending stress divided by Y is equal to your Young modulus divided by R. R is the radius of curvature. Here you should keep it in mind. R is the radius of R. Instead of R you can write as rho. Rho is called radius of curvature, and E is called Young modulus, Young's modulus, okay. Sigma B is called bending stress, Y is called distance. So, that I am just going to show. So, here by this relationship we can find out bending stress is equal to M B Y by I. Here I is moment of inertia, this you should keep it in mind, moment of inertia about x axis. Let us consider this is our z axis and this is our z axis, and this is, let us consider this is our y axis, and the horizontal axis is your x axis. So, if we consider the section of the weld, so this I am just directly showing. Section of the weld. So, what we need to do here, first of all we need to shift this load P, from this S to center of this weld, That means, we need to shift this load P from here to here in this center of this weld, CG of this weld, this you can say. So, if you shift this load from there to CG of this P. So, then what happened, due to the shifting of this load, according to mechanics, what we know? We know that once a load is shift from one position to another position, in that new position there will be a similar load. So, there will be a similar load, P, and there will be a moment, which is there will be a moment, that is your bending moment MB, that will be equal to your load into shifting distance, here is length of the, you can say, load point to weld point, P into L. So, here the bending moment is calculated based on these things. So, here you can say there will be a bending moment, here there will be a bending moment in this weld, MB is equal to P into L. This you should keep it in mind. So, due to shifting of load from one position to another position, there will be a equivalent load plus there will be a moment MB, that is equal to your P into L. This you should keep it in mind. So, here bending moment you can calculate based on this formula. What is P? P equal to your 10 into 10 to the power 3 and L equal to your 200. So, due to this bending moment, what is the bending stress? So, bending stress you can directly find out that bending stress will be what? MB y divided by I x x, that this is your x x, this is our y axis. So, here MB is already calculated, P into L, y will be generally what? Y will be, we can directly call as, generally you see that means this beam diameter by 2, that means radius of this beam, because compared to radius of the beam at this throat thickness is very small, that is why generally we are neglecting those throat thickness T by 2 part, that you can say. Okay. So, that is why we are considering this radius R, okay, divided by I x x, already I have already shown you, this is actually what? Pi T R Q, already I have shown you, that is I x x, how to calculate these things. So, sigma b, by putting all these value, what are the things we can find out? So, sigma b you can directly write as, putting all these value, you can get 1018.59 divided by T in terms of T. Let us consider the throat thickness, is T of this plate weld. This is throat thickness, this you should keep it in mind. Okay. So, this unit is Newton per millimeter square. This is sigma b. This is due to this bending moment MB. This sigma b is coming due to bending moment MB. So, apart from these things, there is a direct load P. So, there will create a primary shear stress. This primary shear stress will be where? In this. So, in this flat weld, generally this bending stress will act perpendicular to the throat section and primary shear stress will be along the throat section, which is this primary shear stress is, here I am writing, due to direct load P, this you should keep it in mind. There will be a primary shear stress, I am representing. So, primary shear stress tau 1 you can write as P divided by throat section area, throat sectional area AT I am writing. So, this weld throat sectional area you can write as 2 pi r into throat thickness. So, if you put the value 10 into 10 to the power 3 divided by 2 pi, here r is 25 divided by t, it is giving us a value, this primary shear stress is 63.66 divided by T Newton per mm square. Okay. Now, so you got this primary shear stress, this show primary shear stress and this bending stress, it is generally act perpendicular to each other, this you can say, this is act perpendicular to each other. So, generally let us consider this is one of the section, I am just taking, let us consider I am taking a small portion from this annular weld, let us say a small portion annular element A. So, in this element generally it is subjected to shear stress, primary shear stress tau 1, which is like this, and there is, due to this bending moment there will be a bending stress sigma b, which is like this, okay, which is normal to each other. Now, from generally to find out the maximum shear stress, if a state of stress is like this, let two dimensional state of stress, this is a state of stress, So, based on this state of stress, we can find out sigma maximum, this formula we know, because if a state of stress is, let this is your sigma y, this is your sigma x, and there is let us tau, there is tau, then according to formula we know maximum shear stress is generally from Morse circle, or for finding out the maximum principal stress or maximum shear stress, we know this formula. So, I am not going to details about the derivation of these things, we know these things, this formula is this. But here you see in this case here you see sigma x you can say equal to 0, and here sigma y equal to generally. So, here sigma x, in this case our sigma x is 0 and sigma y is generally here you can say sigma b, bending stress. So, if we put these things, what we get? Here we will get sigma b by 2 square plus, and tau here is generally given as tau 1 square. So, if we put this sigma b value based on this above calculation, let this is equation number 1 and this is equation number 2. If we put this value, we are getting the sigma maximum value is equal to, you can write as directly, I am just putting, this will be giving us 513.26 divided by T. This is the maximum shear stress. This is unit is Newton per millimeter square. Now, here permissible stress is given as what? 100 MPa. So, here tau permissible given as 100 MPa, this you should keep it in mind. So, this tau max we should compare with tau permissible stress. So, by comparing these things, once we compare these things, what we will get? 513.26 divided by T, this will be equal to your 100. So, from here we can get T is equal to, you can write as 5.13 millimeter, 5.13 millimeter. So, what should be H? So, H will be, you can write as T by 0.707, which will be equal to, you can say 7.26 millimeter. So, this you can consider the next digit full number, that is 8 millimeter. So, this way generally you can find out the dimension of weld once the weld subjected to bending moment. So, next lecture I will discuss about a welded joint which is subjected to combination of this bending moment as well as torsional types of moment. Thank you.